Continuing our discussion on designing an experiment, there are 4 different types of designed experiment: the completely randomized design, the randomized block, matched pair, and repeated measure. And this really comes down to how you are assigning people to your treatment and your control groups, who is going to be the sample in each of these groups. So let's look at the different types of experiment design. So in a completely randomized design, all experimental units have an equally likely chance of being chosen for the treatment group, right? So we basically take a list of people and we are going to then allocate them to the group. So suppose a researcher wants to know whether taking caffeine an hour before swimming affects the time it takes swimmers to complete a 1-mile swim, and that 50 volunteers are available for the study. If we basically take 50 names, put them in a hat, and pull out names, and we pull out one and it gets the caffeine pill, and the next one gets the placebo, and we keep doing that until we have 20 people with the caffeine pill, 25 people with the caffeine pill, and 25 people with the placebo. Then we have all the volunteers swim a mile. Then we compare the two groups. Okay, so completely randomized design. Everyone has an equally likely chance of being in the treatment versus the control. Again, we talked about before, it could be a double-blind study, in which case the people who are assigning them, so you'll have a researcher who is going to determine random chance, so not the researcher themselves saying, you get this, you get that, but pull names out of the hat or randomly generate numbers. One researcher is going to have the list of who's in what group. But then maybe the people who are going to be at the actual event, giving out the caffeine pills, the placebos, they don't know which is which, and the people measuring the times don't know which is which. That would be a double-blind study. Okay, when those who are doing the assessment of the times don't know, and there's separate researchers who are keeping track of who got what. Or a single blind where simply the participants don't know if they got the caffeine pill or the placebo. If the measurements, the assessments that are being done are more subjective, so if we think about not a time, because maybe we could have machines do it. We could have cameras clock how long it takes for people to finish the swim. There, the researcher can't add bias. But if in this process we were going to give a caffeine pill and a placebo, and then do an assessment related to someone's mental health or how positive they felt, and so there are questions by the researcher, or more subjective measurements by the researcher. Well, this person seemed like a 7 out of 10 on a scale for happiness or anxiety. There you want the double-blind study, because the researcher knowing which group they fall into could change whether we assess them as a 6 or a 7 or an 8 on the scale, even if it's an unconscious bias. Okay, so completely randomized design, equally likely chance you're in either group. A single blind versus double blind depends on whether the researchers who are doing the assessment know. Okay. Another example of a completely randomized design, we talked before about 30 teenage girls randomly assigned to 3 diets. And there, we're drawing names out of a hat to determine which diet they are getting. Let's compare that to a randomized block design. A randomized block design, the experimental units are assigned randomly among all the treatments, but separately within each block. So the idea here is we want to make sure that we are controlling for some of those confounding variables. And so what we'll do is we'll have this group has, let's say we're looking at diet pills. This particular group has this BMI. And so from that group, we will then randomly choose one for the treatment and one for the control. So the idea here is to make the groups similar, the control and the treatment group, by making sure there's representation of certain characteristics in both groups. So reducing our variability. So if we go back to our example about the swimmers, right? So we had those 50 volunteers that we're choosing who's going to get the caffeine pill, who's going to get the placebo. If we take those who identify as male and we randomly select for half the male swimmers to be given the caffeine pill and the other half to be given the placebo, and we do the same thing for those who identify as female, then what we've done is we've controlled for gender in the difference, or in terms of what was we were looking at, time it takes for the swimmers to complete the swim, because you don't want it to be based on the reason that they take different times to swim is not based on the caffeine pill or the placebo, but on some other effect like gender. So we can control for gender by having gender be represented in both samples, both the control and the placebo. So then we would compare the times for those given caffeine and not caffeine within each gender, within female, within male, to see if there is a difference. Another example of a randomized block design. So here we're looking at increasing your memorization skills. We want to know if there's greater, maybe age of the participant might be an impact. And so what we would do is classify you into different age groups. So we have the young, the middle-aged, the elderly, and then from the group of young, they are randomly assigned to the treatment and the control. From the middle-aged, randomly assigned to the treatment and the control. This allows us then to compare for this particular subgroup, did our treatment work better for the young people, for the middle-aged, for the elderly? Did the treatment work at all? Because we've controlled for the effect that age might have on memory itself. Another example of a randomized block design. If we're going to look at irrigation on orange trees, the trees in the grove are arranged in 8 blocks to account for a local variation. The blocks are based on the fact that some trees are shaded by a large barn, some trees are close to the river, some trees are planted near a road. So it's quite possible that the location is going to impact the yield, separate from how much irrigation they get. And so we're going to assign the irrigation methods to trees within each block. So those who are near the barn, some will get lots of water, some will get less. Those that are near the road, some will get water, some will get less. So we've controlled for the location issue when it comes to what increases the size or yield of the fruit. Okay. So here would be the data, irrigation method. So notice block 1 might be near the barn, and we then have all these different irrigation methods within block 1. Block 2 might be near the road. We have all those same irrigation methods that were near the barn, but here near the road. And so we can then do our statistical analysis to determine if the difference in these fruit weights is due to location or due to irrigation method. Okay. Another method for designing your experiment is what is called matched pair. In a matched pair design, an individual is selected to receive the 2 treatments in a random order, or we can have 2 matched individuals who are randomized in terms of what order they receive the treatments in. So a matched pair is a special case of a block design. You're still using the randomization to assign the order of the treatments, and you definitely need blinding here to make sure that, one, the participant doesn't know which treatment they're getting, and then you also may have the blinding for the researcher as well, so they don't change how they interact with individuals. So an example, suppose a researcher wants to know whether taking caffeine an hour before swimming affects the time it takes. We have our 50 volunteers. And so what we're going to do is we're going to have our 50 swimmers take both treatments. In the first week, we're going to randomly choose a group to get the caffeine pill. We're going to randomly choose a group to get the placebo, and we're going to have them swim the mile, and we're going to see how long that takes. Then in week 2, we'd repeat the process, but then give them the other. If they had the caffeine pill the first time, we give them the placebo. If they had the placebo the first time, we would give them the caffeine pill. So their idea there is we've controlled for everything because it's the same person. And of course, it's only going to work if something has a short-term impact on that. So we can compare for that person, is there a difference in their swim time between the two? Another example would be like a pre and a post test. So we could let's just talk about outside of medical experiments. What about in terms of education, right? So I could give you a quiz and see how well you do. And then we could do an activity, and then we can measure how well you did after that and measure the change for each person pre and post, where the activity is in between. To do a really refined study, we would have some of the group if we're measuring multiple effects, if we're measuring reading the book versus doing a class activity, we would then we'd give you a quiz, see what you know, nothing. You read the book, see what you know now. For others, we would have you do the activity. We could compare change over time, pre and post. We could compare the two different treatments. If we were going to compare both the change in knowledge from the reading the book and the activity, some of you would have to do the activity first, then the reading, and some reading and then activity. So how you're designing this depends on what you're trying to measure. Are we trying to compare change over time with a pre and a post? Are we trying to compare different treatments? In this particular example you see here, we have 15 animals whose pulse rates are measured before and after the administration of a drug. So we want to know, is the drug changing their pulse? And so they're all getting the treatment because we can then measure how each of them change before the drug and after the drug. All right, so just to recap a bit where we've been talking. Okay, we talked about completely randomized design, randomly select people for the treatment and for the control, randomized block where we take certain characteristics and randomly select from middle-aged people to be in each group, elderly people to be in each group, and now we can control for some of those otherwise confounding variables. We talked about the match pair, that's the pre and the post. We look at how something changes for the same person. Repeated measure is where we are going to measure repeatedly over time. So think about the pre and post, they paired, and we're just going to do more of it. So it's a special case of blocking. One participant's measurement constitutes a block. So an example here of a repeated measure, a pharmaceutical company examines the effects of 3 drugs on respiratory ability of asthma patients. The drugs are randomly assigned to 24 patients each. The assigned drug was administered. Then we measure respiratory ability, volume of air that can be forced out in 1 second after taking a deep breath. It's measured hourly for 8 hours following the treatment, and it's measured immediately prior to the administration of the drug. So we're not just doing a pre and a post, we're not just measuring before and after, but repeated measures. And so we then have that a single individual is in samples based on time, right? So we have a lot of different groups, but the same people are in every one of those groups. So for example, here we go. We have a base measure, a 1 hour measure, a 2 hour measure, a 3 hour measure, a 4 hour measure. And so we're repeating it many times across time. So we had a repeated measure where we're taking information from an individual many times. A matched pair where we are looking at like a pre and a post, so before and after some kind of treatment. We have our randomized block and our completely randomized design.